In this lesson, we'll extend our integration techniques by talking about integration by substitution. Now, this is the last integration technique we're going to talk about in this course, but in Calculus 2 there are several more integration techniques that handle things such as products and other types of functions too. Integration by substitution is actually the reverse of the chain rule. I'll give you guys a little description of what is going on here, and then I'll give you several examples. I will say integration by substitution, also known as the substitution rule, is a very tricky concept. You're going to want to practice and practice and practice. I'm going to tell you now, if you can't calculate an antiderivative and you can't calculate a regular derivative, you are already in trouble. However, this is something that can be done. You just need to make sure that you know the background already. With that said, here's the substitution rule. What you do is you look for some function g of x, which we often just call u. It's some part of the function that's inside of another part of the function. So if you call that u, what you then look for is the derivative of u. You see if you can somehow get that derivative in the problem. If it's not there, your choice of u won't work. But if it is there in some form, then you can make a substitution and just call g of x now u. The g prime of x will disappear, and we'll just call it du. This literally is the inverse, or the idea of the chain rule, in that the derivative of f of u would be the derivative of the outside times the derivative of the inside. That's the idea. We pick some part, call it u. The strategy is after we get u, we calculate the derivative of u and we call that du. Call it du and just calculate the derivative, and we put a dx on the end. Now the fact that there's multiple d things floating around is exactly why I warned you early on. Don't leave off your dx's, because now you're going to have to deal with two of them and you want to be very careful. So what we do is we make a new integral. We substitute in for u and for du, and then we integrate that thing. It should be easier than it was before, and then we back substitute. We change u back to x and we get an answer. I can describe this till I'm blue in the face, but I think examples will do this tremendous justice. Here's our first example. What you notice is that there's a square root of something. Now if you recall where the chain rule came in, anytime a function would technically need the chain rule or some part of it, then you probably need substitution. Not always the case, but often. I'm going to choose this to be my u because it's inside the square root. It's a part of a function inside of the function. So if I let u equal x squared minus x, then what I do is I now calculate du. Du is 2x minus 1 dx. This is the notation. I just take the derivative of x squared minus x, I get 2x minus 1, but I write it as du is the derivative times dx. Now here's what I'm looking at. Let's look back at the integral. 2x minus 1 is right there, as is the dx. So what I'm going to do is I'm going to make a straight substitution. You've got x squared minus x is my u, and this part, the 2x minus 1 dx, is going to become du. Now I have a new integral. This part is gone because it's going to be at the end with du. What I had left now is the square root of u, du. I've got a new integral. What I need to do now is integrate this thing. Let's find the antiderivative. So this is u to the 1/2, just rewriting it. And we know by our power rule that we're going to raise the power by 1 and divide by the new power. And since that was an indefinite integral, we include a plus c. I'll rewrite this as 2/3 u to the 3/2 plus c. And then we get 2/3 u is x squared minus x. So once I have a final answer in terms of u, I plug in what u was. X squared minus x to the 3/2 plus c. So back substitute at the very end to get a clean final answer. Next example. You could in theory do this yourself, but you would have to raise this to the 45th power and it would be a nightmare. I notice that there's an x squared plus 1 inside the power. Let's call that my u. U is equal to x squared plus 1. So du is 2x as the derivative of this thing, and I need a dx. Now I'm going to use both of my equations. I've already got my u in place, and sure enough, hey look, 2x dx. That's going to be my du, this 2x dx. 2x is going to disappear. It's going to become part of my du, and all I'm left with is u to the 45th du. Now, take a look. U to the 45th is a very easy integral for us to do. Just use the power rule. I get u to the 46 over 46 plus c. And now back substitute. X squared plus 1 to the 46 divided by 46. Just simply change u back to what it was before. Before we move on, let's summarize our steps again. Pick u. Find a u that's inside the function. Calculate du by calculating the derivative and writing it with a dx. Substitute both equations into the integral. Both. You must use the u and the du equation. Substitute both equations in. That's step 3. Integrate. Got to do that integral step. Students, for some reason, forget to do this sometimes. Integrate. Use your integral rules. Then back substitute. We're going to let u equal the exponent, the x squared minus 3. That's often a good choice. Du equals 2x dx, and since we don't have the 2, we'll just go ahead and divide by 2. We get x dx. We get e to the u, and then the x dx becomes du over 2. Here we have it. The du over 2, I'll bring the 1/2 in front. We're just left with the integral of e to the u du. Well, again, this is nice and easy. The integral of e to the u is e to the u plus c. So we get 1/2 e to the x squared minus 3 plus c. A lot of times when you do things with e, the e sticks around with exactly the same powers. Next example. X squared minus 3 is going to be my u because it's inside the function pretty deep. So I'm going to let u equal x squared minus 3. So du is 2x dx, taking the derivative. Now this time I've got a 4x in the way. That's a little bit on the odd side. So what I'm going to do is I'm not going to overcomplicate this. I'm just going to go ahead and divide by 2 anyway. I get du over 2 is x dx. Let's see what we get here. X dx is going to become du over 2. Now if you want, you can play around with it. If you have some insight as to how you could have done this differently, feel free to use it. I just don't want to confuse anybody. What happens is I still have a 4 this time. The x is going to become part of my du, but I do get the square root of u. And I get du over 2. Rewriting that, I'm going to bring this as a 1/2 in front. That gives me a 2 in front. Got u to the 1/2 du. I just did this one a minute ago. What I ended up with was 2/3 u to the 3/2. Let's just reuse that result. Plus c since I just integrated. So I get 4/3. U was x squared minus 3. And that's raised to the 3/2 power plus c. Find something to call your u. Calculate du. Plug both into the equation. Integrate and back substitute. Now for this one's not obvious what to do. However, here's my thought process. Sometimes the denominator is a good choice. Unfortunately, we're still kind of in a circumstance where letting it be tangent cubed x would not be a good choice. However, I noticed secant squared x up there. Recall that the derivative of tangent of x is secant squared x. So what I'm thinking about is well, maybe if I let u be tangent of x, A bit unconventional, but why not? If I let u be tangent of x, then du is secant squared x dx, and I can make du immediately from what I'm given. There's my du. Here's what I end up with. Secant squared dx is going to become du. I will tell you right now, I never write du in the numerator, though you will sometimes see it. I'm just going to have a 1 over. Now tangent cubed x, if you recall, that means tangent of x all cubed. So now I get u cubed. To integrate this, I'll write this as u to the negative 3 du. Power rule changes this to negative 3 plus 1 is negative 2. And then finally, let's rewrite it as negative 1 over 2u squared. So I can back substitute and get negative 1 over 2 tangent squared x plus c. All the idea is pick a u so that you can make du. This will come with practice. The more practice, the better you'll do. Next example. I see a square root of x inside these parentheses, so let's call that my u. So if I let u equal the square root of x, then recall this formula that I gave you. The derivative would be 1 over 2 square root of x. That's a very useful formula. It's just handy all the time. Now I don't have a 2 in this problem at all, so let's multiply both sides by 2 and get a cleaner equation here. How am I going to use this? I got a square root of x down here, which is in the denominator, but really this is exactly what I want. This is 1 over the square root of x. So actually this right here is going to become my 2 du. All that's going to become 2 du, and I'm just left with sine u. Integral of sine u is negative cosine u. Got a plus c now. And so I have negative 2 cosine of, let's see, it was square root of x plus c. Two more examples. E to the 2x will be my choice of u. Why? Because it's inside the sine function. Then du actually requires the chain rule. It's like an e to the u, so I get e to the 2x, but times the derivative of 2x. Du is 2e to the 2x. That's the derivative of 2x, dx in both of these. E to the 2x dx I have, but not the 2. Let's divide by 2. I get sine of u, and this part is du over 2. I get the integral with a 1/2 in front of sine u du, which is 1/2 times negative cosine u plus c, and back substituting and cleaning it up a bit, I get negative 1/2 cosine of e to the 2x plus c. Next one, we've got an x cubed minus 3. So if we let u equal x cubed minus 3, because it's in the exponent here, then du is going to be 3x squared dx, and I have an x squared. So du over 3 equals x squared dx. We've got a u here, and du over 3 is this part. We get a 1/3 in front. Integral, let's see, x squared dx goes away, and we're just left with 2 to the u du. The rule is 2 to the u becomes 2 to the u over natural log of 2 plus c. Simplifying that a bit too, I get 2 to the x cubed minus 3 divided by 3 natural log of 2 plus c. Let's talk about this in general. There's 3 ways that you're going to choose a u. The most common way is just simplifies the expression and easily makes du. So pick a u that's just kind of inside the problem. It would be really nice if I got rid of it, and we'll see from there. Sometimes you would choose a u based on what du you can make. Sometimes it's just tricky. The u just doesn't work. You just can't make du with that choice. And we'll do more of that in chapter 5 when we have some new problems for this. And then type 3 is maybe you can simplify a part of the expression, but there's still something extra. Let me give you guys an example of this. The clear choice here is let u equal x minus 1. Well, if u equals x minus 1, then du is just equal to, well, 1 dx. I'm just going to call it dx. Here's what happens. This becomes du. But what about this x? What do I do with it? This is what we do with it. If you have an extra x or something similar floating around, take your equation and solve for x. X equals u plus 1. Well, let me mark that here. I get the integral of u plus 1. And then I get the square root of u. And then I get du. So to simplify this, let's do u plus 1 times u to the 1/2. So that I can now distribute this and get u to the 3/2 plus u to the 1/2. And then we will use the power rule. I get u to the 5/2 when I add 1 to the power, divided by 5/2, plus u to the 3/2 when I add 1 to the power, divided by 3/2, plus c. So rewriting that, I get 2/5. U was x minus 1 to the 5/2, plus this becomes 2/3 x minus 1 to the 3/2, plus c. And that's probably the easiest way to solve this problem. If you have an extra x, solve for x in your u equation. Use that. Sometimes you need it. Not too often, but sometimes. Now just one more thought of one thing that we can do is u-substitution when we have a definite integral. Now there are some conditions on this, but what it boils down to is do your u-substitution like normal, but you change your limits. You actually plug these x values in to the u function to get new values. The idea for this is that you would do it just like you would an indefinite integral, but you're going to change your limits of integration in the process. There's two differences. One, you get a brand new integral. You don't have to back substitute. You get a new integral, you just ignore the old integral entirely, which is kind of handy. You just solve the integral, be done with it. Another one, and this is careful notation here, if you don't change your limits, you need to use an indefinite integral. Do a whole problem on the indefinite integral, then go back to your original problem to finish it. It's a notational issue that is a bit of a critical difference. You don't want to write a definite integral and do a u-substitution with the old values because that sort of means they're in terms of u and they're actually in terms of x. Don't change the limits and back substitute, and don't do a u-substitution without changing the limits unless you're doing it as an indefinite integral. Let's do a couple of examples of this. I'm going to let this be my u, just inside the problem as usual. If u equals 1 plus x cubed, then du is 3x squared dx. So since I don't have a 3, I'm going to do du over 3 equals x squared dx. The x squared dx is going to become du over 3. Now let me give you guys the usual strategy. This du over 3 is going to show up all the time. I'm just going to go ahead and write it in front. Going to leave this integral alone for a second. I'll put some numbers in a moment. I get u to the 5th du. Now here's the strategy. Here's the difference. I cannot write 0 and 1 right now. That is incorrect notation because those were values in terms of x. I need values in terms of u. So what I'm going to do is plug in 0 from right here into the equation for u, which is 1 plus x cubed. 1 plus 0 cubed is equal to 1. And then I'm going to do the same for 1. I get u of 1 is equal to 1 plus 1 cubed, which is 2. So 0 changes to 1, and 1 changes to 2. Brand new integral. I no longer have to back substitute at all. There's no reason to. I simply get, still got a 1/3 in front, u to the 6th over 6, evaluated from 1 to 2. Do it as if I never had an integral at all with x. Because I changed my limits, I can just calculate the number. This is really a 1 over 18, and then I get 2 to the 6th minus 1 to the 6th. Now I used a little technique there that I haven't mentioned to you guys. If you get a number in front, you can just leave it in front and just do the subtraction on the inside. No problem with that. So I get 2 to the 6th is 64 minus 1 is 63 over 18. Both of those are divisible by 9, and I get 7 over 2 as my final answer. For the next example, we're looking back at e to some power. Remember, when you see e to some power, your best choice for u is whatever is in the exponent. So I'm going to let u equal sine x. Then du is its derivative, cosine x dx, and I really don't have to do anything with what I have here to make this work. Cosine x dx has no special constants. This is just immediately my du. But now let's also change our endpoints. If I plug 0 into the u function, that's going to be the sine of 0, which is 0. If I plug in pi over 2 into the sine function, I get the sine of pi over 2, which is 1. Now if I change my whole integral, 0 became 0, pi over 2 became 1, and I'm just left with e to the u du. Now let's integrate. The integral of e to the u is still e to the u. That's going to be evaluated from 0 to 1. So I get e to the 1 minus e to the 0. And then the last thing I'll do to simplify this, e to the 1 is just e to the 0 is 1, and I'll just say e minus 1. No need to back substitute because you changed your limits. Even and odd functions. An even function has the property that f of negative x equals f of x. We talked about this a little bit in college algebra. Odd functions have the property that f of negative x is equal to the negative of f of x. This is the idea of y-axis symmetry and rotational symmetry around the origin. When we have these particular properties, and we're taking the integral from negative number to the same number but positive, we get some nice things. If we have an even function, that means it has symmetry on the x and y axis. What that means is that the area to the left of 0 and the area to the right of 0 are the same. All you have to do is calculate the area from 0 to a and multiply the answer by 2. Handy. If you have an odd function, it's even nicer. Because of the rotational symmetry, the area on the right side is going to be the same as the area on the left side, but the negative area will show up on the left side. Or possibly the right side's negative and the left side's positive. But either way, you add the negative and the positive, and you get 0. Very helpful. For an odd function, the integral just turns out to be 0. Now just keep those tricks in mind that you can answer instantly if you remember that the integral of an odd function from negative number to a positive number is 0.